Good morning, everyone. Welcome to the course Stability Aspects of Structural Steel Design, Concepts and Applications. In this session, we will talk about Perry-Robertson approach. In practical scenario, perfect columns do not exist in actual engineering structures. What are imperfections? Deviations from ideal column condition. Imperfection can be classified into two categories. One is imperfections in geometry, another is imperfections in material. Imperfections in geometry basically relate to initially bent crooked columns, which is handled by Perry's formula, or it can be eccentrically loaded columns handled by secant formula. As you can see, the geometric imperfections at the member level. Imperfections in material primarily result in residual stresses due to manufacturing, especially hot rolling as well as welding. Here you can see the stress strain plot. For a coupon test, it follows a bilinear stress strain curve, whereas for a stub column, you can see that it is straight up to sigma p, which is linear, and after that it deviates away from the bilinear stress strain curve and then later joins the yield value sigma y, which can be seen in the red color dotted lines. This imperfection, which is material in nature, is at the section level. Typically, practical columns will have both the types of imperfections. So, the column strength is primarily affected by two types of imperfections. They are initial out of straightness as well as residual stress. The approach which combines both of them is the Perry-Robertson approach. Now, let's look at the Perry-Robertson approach. But before that, let's look at Perry's formula. So, Perry-Robertson approach is an elastic approach based on the failure of the extreme fiber when the stress reach yield. It is a combination of initial out of straightness as well as material imperfection. Recall, the initial out of straightness is given by the Perry's formula. The initial out of straightness is based on the initially bent shape of the column, whose lateral displacement is y0. However, when load is applied, it moves from y0 to y0 plus y. So, we have y0 is the geometric imperfection described in a sinusoidal fashion is equal to a into sine pi x by L, and y equal to alpha by 1 minus alpha into a sine pi x by L. Yt is equal to a by 1 minus alpha into sine pi x by L. All these derivations have been covered in the previous sessions, where alpha equal to p by p Euler, which is given as p sub e. The initial deformation at midspan y0 equal to delta naught at x equal to L by 2. y0 equal to a into sine pi x by L, delta naught equal to a into sine pi into L by 2 divided by L. So, which gives rise to the value delta naught equal to a, which means that the maximum imperfection at x equal to L by 2 is a. Also, the deformation due to applied load P is given as at x equal to L by 2, y equal to delta, which means that y equal to alpha by 1 minus alpha into a sine pi x by L, and instead of x we put L by 2, we get delta equal to alpha by 1 minus alpha into delta naught. So, the deflection and midspan gives rise to delta naught equal to a, which is the initial imperfections, and delta equal to alpha by 1 minus alpha into delta naught. The total displacement is given as y0 plus y, which is given as delta t equal to delta naught plus delta. So, we have yt equal to a into 1 minus alpha into sine pi x by L. So, delta sub t is equal to delta naught divided by 1 minus alpha into sine pi L by 2 by L, which gives rise to the value delta t equal to 1 by 1 minus alpha into delta naught. The extreme fiber stress of a member which is subjected to both axial and flexural load is given by P by A plus My by I. The P by A represents the axial load and My by I represents the bending stress. When we add the two, the extreme fiber stress is happening at the top, and it happens at a distance of y from the centroid of the cross section. So, the extreme fiber stress is given as P by A plus My by I. At midspan, we know that m equal to p into delta naught plus delta. Substituting I equal to ER square and m equal to p into delta naught plus delta, we have the extreme fiber stress as P by A plus p into delta naught plus delta into y divided by ER square. We have P by A plus p into delta total into y divided by AR square. The delta total is represented as delta naught plus delta. We also know that the delta total is given by 1 by 1 minus alpha into delta naught. And here in this equation, we can reformulate this one by stating that the extreme fiber stresses is equal to P by A plus P into delta sub T divided by A into R square by Y. So this R square by Y can be replaced as C, and by substituting delta sub T equal to 1 by 1 minus alpha into delta naught, we get this equation sigma extreme fiber is equal to P by A plus P by A into 1 by 1 minus alpha into delta naught divided by C. We introduce the parameter eta equal to delta naught by C, where eta is the non-dimensional imperfection parameter. Now let's look at how is it non-dimensional. So the unit of delta naught is in distance, which is mm, and the unit of C is r square by y, so millimeter square by millimeter, again in mm. So the unit of eta equal to mm per mm, which becomes it is non-dimensional. Therefore, sigma extreme fiber is equal to sigma plus sigma into 1 by 1 minus alpha into eta. We have changed P by A as sigma. Now, we have to recall that alpha equal to P by P sub E, which is the ratio of applied load with respect to the Euler load. So, the extreme fiber stress is equal to sigma plus sigma into 1 by 1 minus P by P sub E into eta. This can be further simplified because P by P sub E can also be written as sigma by sigma sub E, as you can see on the right hand side of the equation. On further simplification, we have sigma extreme fiber stresses is equal to sigma plus sigma into sigma E divided by sigma sub E minus sigma into eta. The sigma sub E corresponds to the Euler buckling stress. So the extreme fibers is equal to sigma exterior equal to sigma into 1 plus sigma sub E divided by sigma sub E minus sigma into eta. Now let's look at the failure criteria. So we consider the column has failed when sigma extreme fiber reaches sigma sub y. So the corresponding stress sigma sub P is given by sigma y is equal to sigma into 1 plus sigma sub E divided by sigma sub E minus sigma into eta. Taking sigma equal to sigma sub P, which is the stress corresponding to the proportional limit, we have sigma y equal to sigma P plus sigma P into sigma E into eta divided by sigma E minus sigma P. We can take this to the other side, which becomes sigma y minus sigma P is equal to sigma P sigma E into eta divided by sigma E minus sigma P. This becomes the Perry's formula, which is sigma y minus sigma P into sigma E minus sigma P is equal to eta into sigma P sigma E. This is a quadratic equation of sigma P. So we can expand this quadratic equation, which gives rise to the equation sigma y sigma E minus sigma y sigma P minus sigma P sigma E plus sigma P square is equal to eta into sigma P sigma E. So we can further simplify this by taking sigma P sigma E to the right hand side. We have sigma y sigma E minus sigma y sigma P plus sigma P square is equal to 1 plus eta into sigma E sigma P. This again can be further simplified by taking sigma y sigma P to the other side as well. So in the left hand side, you have sigma y sigma E plus sigma P square is equal to 1 plus eta into sigma E sigma P plus sigma y sigma P, which can be further simplified in the form of a quadratic equation sigma P square minus of 1 plus eta into sigma E plus sigma y into sigma sub P plus sigma y sigma E is equal to 0. Here, the value of sigma P equal to minus B minus root of B square minus 4 into sigma y sigma E by 2. This is the smaller root in the quadratic equation, where B equal to minus of 1 plus eta into sigma E plus sigma y. Now we have sigma sub P equal to 1 plus eta into sigma sub E plus sigma sub y minus root of 1 plus eta into sigma E plus sigma y the whole square minus 4 into sigma y sigma E by 2. This can be further simplified by dividing this equation by 2 and taking sigma y in common terms. We have sigma P equal to 1 plus eta into sigma E by sigma y plus 1 bracket close sigma y by 2 minus root of 1 plus eta into sigma E divided by sigma y plus 1 by 2 the whole square into sigma y square minus sigma y sigma E. The term inside the root of the bracket can be further simplified by multiplying by sigma y and dividing by sigma y. For making things much easier, we have sigma p equal to 1 plus eta into sigma e by sigma y plus 1 into sigma y by 2 minus root of 1 plus eta into sigma e divided by sigma y plus 1 by 2 the whole square into sigma y square minus sigma y square into sigma e by sigma y. On further simplification, we take the sigma y outside, so the equation looks the one as you can see from the right side. And dividing the entire equation by sigma y on both sides, we have sigma p by sigma y is equal to 1 plus eta into sigma e by sigma y plus 1 divided by 2 minus root of 1 plus eta into sigma e by sigma y plus 1 by 2 the whole square minus sigma e by sigma y. Introducing the terms n equal to sigma sub e by sigma sub y and lambda equal to root of sigma sub y by sigma sub e, which gives rise to the value n equal to 1 by lambda square, which implies sigma e by sigma y equal to 1 by lambda square. Now substituting it back in the equation, we have sigma p by sigma y equal to 1 plus eta into 1 by lambda square plus 1 divided by 2 minus root of 1 plus eta into 1 by lambda square plus 1 divided by 2 the whole square minus 1 by lambda square. So we have now sigma p by sigma y equal to 1 plus eta plus lambda square by 2 minus root of 1 plus eta plus lambda square by 2 the whole square minus 1 by lambda square. We can further simplify this as you can see from the right hand side of the equation. The equation can be further kept in a concise form by introducing the term phi, where phi equal to 1 plus eta plus lambda square by 2. Now this gives rise to the equation sigma p by sigma y equal to phi by lambda square minus root of phi by lambda square the whole square minus 1 by lambda square. We multiply and divide by phi by lambda square plus root of phi by lambda square the whole square minus 1 by lambda square. When we do so, we use the term a minus b plus a plus b is equal to a square minus b square. So we have sigma p by sigma y equal to phi by lambda square the whole square minus root of phi by lambda square the whole square minus 1 by lambda square the whole square divided by phi by lambda square plus root of phi by lambda square the whole square minus 1 by lambda square. This again boils down to sigma p by sigma y equal to phi by lambda square the whole square minus phi by lambda square the whole square minus 1 by lambda square divided by phi by lambda square plus root of phi by lambda square the whole square minus 1 by lambda square. On further algebraic simplification, we have sigma p by sigma y equal to 1 by lambda square divided by phi by lambda square plus root of phi by lambda square the whole square minus 1 by lambda square. We take 1 by lambda square common, we have sigma p by sigma y equal to 1 by lambda square divided by phi by lambda square plus root of phi square by lambda power 4 minus lambda square by lambda power 4. We have basically multiplied and divided by lambda square on the previous equation so that we can take lambda power 4 outside, and hence we have this equation here which further simplified, and we now can conveniently take 1 by lambda square from the numerator as well as the denominator, and we get this boiled down equation which is sigma p by sigma y equal to 1 by phi plus root of phi square minus lambda square. So this equation is also known as Perry's formula, becomes an empirical formula when we adopt Robertson's definition of the imperfection parameter eta, and 0.003 in the Robertson expression is referred to as the Robertson constant. So the Perry-Robertson formula is of the form sigma y minus sigma p multiplied by sigma e minus sigma p is equal to eta into sigma p sigma e, where eta equal to 0.003 L by R instead of eta equal to delta naught by C. So we have phi equal to 1 plus eta plus lambda square by 2. Lambda square is equal to 1 by n equal to sigma e by sigma y. The non-dimensionalized imperfection parameter eta equal to delta naught by C, where C equal to R square by y, which implies C equal to I by A into y because R square equal to I by A. And we also know that I by y equal to the section modulus Z, so C equal to Z by A. Here, eta is the non-dimensional imperfection parameter, which is a function of section dimensions, as well as delta naught, which in turn is a function of A, which is the amplification factor. So this depends upon the type of imperfections. and the magnitude of imperfections, which is very hard to predict. So note that eta in Perry-Robertson formula is empirically arrived at, and it allows for all other imperfections in addition to delta naught that might be present in the columns. So the imperfections is equal to geometric imperfections, which is delta naught, plus material imperfections as a result of residual stresses, plus any other deviation from the ideal Euler column strut. So now what happens when the imperfection, that is eta, increases? So taking eta equal to beta into L by R, expression which is very suitable for curve fitting. We have this plot here, which is the non-dimensionalized stress in the y-axis and the non-dimensionalized slenderness in the x-axis. We have various values for beta. So when we put beta equal to 0.003, now when we decrease the imperfection from 0.003 to 0.001, you can see that the blue color line is at the top. And then when we slightly increase it from 0.003 to 0.0035, you can see a red color line at the bottom. And we further increase it to 0.0055, which is the yellow color curve. And we increase it further by putting a value of beta equal to 0.008. We have a dark green color curve. And the Euler curve, as usual, is shown here. What is most important to understand here is that when we increase the imperfection, which is a function of beta, we can see that the curve slowly changes from convex to concave, which means that lower imperfection leads to higher buckling capacity and higher imperfection leads to lower buckling capacity. So the load carrying capacity of a column decreases as imperfection increases. So IS 800-2007 adopts Perry-Robertson approach for design of axial columns. Section 7 of design of compression members indicates the same. We have the design compressive stress FCD of axially loaded compression members shall be calculated using the following equation. This equation is the same as the equation that we recently derived, which you can see from the left hand side. And the parameters are also shown very similar to what we have done. And you can see that the phi is the same, almost the same as the one on the left hand side. When we compare the two, we have eta equal to alpha into lambda minus 0.2, where alpha is also known as the imperfection factor, which is given in table 7 of IS 800. It is a function of the buckling class A, B, C or D, and the alpha value increases with increase in buckling class. So as alpha increases, imperfection increases. When imperfection increases, the load carrying capacity decreases. Now, it can also be represented in figure 8 of IS 800. You can see that the 4 types of curves A, B, C and D, similar to what we have seen previously. As alpha increases, the imperfection increases. When imperfection increases, the load carrying capacity decreases. So this alpha, which we have been talking about, is a function of the buckling class. Here, eta equal to alpha into lambda minus 0.2. How did we come up with this equation? We will answer this question in the upcoming slides.